Hi. So today we're gonna talk about t-tests and z-tests. First, we'll be talking about all sorts of concepts that we need to know before we talk about t-tests, and then both basically t-tests and z-tests use the same concepts. They're a little different, but we'll be talking about the concepts first, and then what t-tests mean and what z-tests, how they are different from t-tests. So first we have types of tests. Tests can be of two types. First one is a parametric test and the second is a non-parametric test. So a parametric or a test makes assumptions about your data, which is why it is known as parametric test. So it assumes that your data has a fixed mean and variance, and that your distribution follows a normal distribution. When you make the normal distribution of any data or any variable, if it follows a bell curve of this form that you can see here, there's a bell curve, right? So if your data follows this kind of a distribution, it is known as a normal distribution. And then we have non-parametric tests. Non-parametric tests cannot make the same number of assumptions as a parametric test. Parametric test will assume that your data has normal distribution. It is usually consists of an independent variable and identically distributed, has constant mean and variance. I mean, it has three main assumptions that it makes about your data. But non-parametric tests cannot say that. Non-parametric tests usually deal with ordinal data or data that cannot be classified into a normal distribution like the parametric test. So you can see in a parametric test like a chi-square test here that's shown. So you can see that on the left hand side, this column, it shows A, B, and C, and on top we have it is compared with two values black and white. So these are not normal numeric data, these are ordinal data. So it can be values, any sort of data which will not follow a normal distribution. That is why for these kind of cases we use non-parametric tests. Non-parametric tests are obviously going to have lesser power because these tests um, do not make as many assumptions as a parametric test. Okay, now coming to hypothesis testing. So statistics is built around the concept that we have a hypothesis that we need to test. If we do not have a hypothesis, statistical tests would have half the meaning of what they're used for. So in any test or any study, we will have a hypothesis that we are going to test, which is called the null hypothesis. So we wish to prove this wrong. We want to compare, let's say we have data that's corresponding to the standard pH level of water in a certain area, and there is already some data available that the pH of water should be, if it is around 7.5, then it is ideal. If it is not, then it is different, it is not ideal. So if we want to test the data, if you want to test the water salinity or the pH level from a certain region and compare it to this available data, then we are going to use null hypothesis that our the salinity or the pH level of the water that we have collected, the data available, the overall pH level is equal to the mean 7.5. That will be a null hypothesis. Now, what is alternative hypothesis? Is it something different? Yes. Null hypothesis is what we are testing. If our results are not what we assume, we have assumed that, let's say in our case, the data of 7.5 is the same as the pH level of the water that we have collected. But if it's not the same, that means then we can reject the null hypothesis and we can accept the alternative hypothesis that the pH level of the water of the region that is selected is different from the actual or estimated or assumed pH level of generally of water. So if there is a hypothesis that we accept in case the null hypothesis is rejected is also called as alternative or research hypothesis. Now, what is a test statistic? Test statistic is any value that we get from a test. Let's say a t-test would give us a t-statistic, a z-test would give us a z-value. So often these values are going to be used to finally calculate the probability or the p-value, which decides the result of our statistical test. So it is a number it's going to come in the form of a number, and the p-value or the probability of our result is going to determine whether to reject or accept a null hypothesis. Okay, now we come to rejection region. Rejection region is very important because it is a region where if our values that we saw in the last slide, if the test statistic value falls in a certain region, then we will reject the null hypothesis. We calculate the p-value. Now, where do we know what is the region that the p-value should fall in so that we can reject the null hypothesis? That is called the rejection region. So the critical region or the rejection region is where our p-value or the test statistic value should fall so that we can reject the null hypothesis. Remember, we are always trying to reject the null hypothesis, and what we are actually trying to prove is what we're going to put in the alternative hypothesis. We cannot accept the null alternative hypothesis unless we are able to reject the null hypothesis. So defining a good rejection region is very important. So as you can see in the bell curve over here, we have a rejection region on both the tails of the bell curve. So if our value, let's say we get a really small value of 0.1, and we have said that this region is defined by 5% of the bell curve on each side. This is 5% and this is 5%. So both the rejection regions are a total of 10% of the bell curve. So if our value, p-value falls within this region, then yes, we can reject the null hypothesis and accept the alternative hypothesis. Okay, so now that we know what are the tests, what kind of hypotheses are there, we know that we are going to be using a parametric test because our t-test is a parametric test. We know that we have to set a null hypothesis, an alternative hypothesis, and we are also going to define a rejection region. Now, when you do a t-test, it is important that you have two groups available. If you have more than two groups, you're obviously going to go for an ANOVA test, which is similar to a t-test, but it deals with more than two groups. Now, if you're dealing with two groups, it could be possible that you have to compare the value of a group and with one value, with a single standard value, or you're comparing the means of two groups, or you're comparing the mean of the same group over a period of time. So those can be called, can be separated, or you can classify them into one sampled, independent samples, and paired samples tests. So let's see what these are. Okay, so one sample test basically deals with comparing the population. So we have a population over here, as you can see, a really large crowd, and we have a sample from that, a sample of, let's say, children from this huge crowd, and we are going to compare the mean of this sample in the sense a really small number, because we cannot calculate the mean of the entire population. That's going to be a humongous amount of data. So t-tests, basically these kind of tests help us find the results of our test with a small sample, and we can later apply the result to a larger population. So one sample t-test basically compares the t-value of a small population, such as the sample of these children or any small group, with a standard value, let's say the pH level of water or the temperature, average temperature of a certain region. So those kind of values are called as standard values. And if you compare them with just one sample of data, then that is called a one sample t-test. So what is an independent samples test? So independent samples basically deals with two different populations. If you have two different populations, like assume that you have, this is the right hand side picture deals with people from Europe and the left hand side picture deals with people from America. So if you're going to compare the population, the means of the two populations, then that is called an independent samples test, because the two populations are different. They are vehemently, they're absolutely different. There is nothing common between them, but you are going to check some sort of value. You're going to compare the means of these two populations, obviously by using samples. So that's why it's called independent samples test. Okay, now we have a paired t-test. So we saw in the beginning that we had a group of children or a small group or sample of the data, and let's say we have to compare this value with the same population or the same sample, but the values of the population or the values of the samples are changing over time. Let's say you have real-time data. It's an example where across the internet we have various websites where data that's coming into the website is changing over time, over every second, even data from sensors or such kind of data where it's real time enabled or it's changing over time. So those kind of data, you can see that the data is still it's belonging to the same sample. So when you have the same sample, but you're just going to compare the values over time, it's called a paired t-test. Okay, now we have types of t-tests. We have seen one type of t-test, one classification, that was one sample, two sampled, or independent samples, and paired samples. Now there's another classification of t-test, is either we take a one-tailed or a two-tailed t-test. As you can see here, if we consider just one end of the bell curve, it's called a one-tailed t-test. But if we consider both the tails of the bell curve, then it's called two-tailed t-test. Now let's say, for example, we have an example. Now, for instance, assume that we have two groups of flowers and we have to compare the petal length. If we compare the petal length, our null hypothesis is going to be that if they have the same petal length, they're going to be of the same species. So if we want to just check that they're of different species, then we are going to use a two-tailed bell curve or a two-tailed t-test. The value can lie in any of the tails, but if it does, it just tells us that the two groups are different. Now assume that our null hypothesis says that since the petal length is the same, both are of the same species and it is of this amount of length, let's say 5 centimeters. Now, if we want to know if the yellow flower's petal length is greater than the pink flower's, then we are going to use a one-tailed t-test. If we need to measure the direction of inequality, how much inequality is there, then we are going to use a one-tailed t-test. If we just want to know if the two groups are different, then we will use a two-tailed t-test. So now that we have an idea of what a t-test is, how you would select a t-test, let's come to what is the formula of a t-test. So t-test is basically comprising of x1, the mean of the first group, subtracted from the mean of the second group. I'm sorry, the mean of the second group subtracted from the mean of the first group. So x1 bar minus x2 bar, whole divided by the radical or the square root of the standard deviation. S basically indicates the standard deviation or the standard error of the two groups, multiplied by 1 over n1, the number of samples in the first group, plus 1 over n2, that is the number of samples in the second group. So as we saw from the previous slide that after plugging in all the values of x1 bar, x2 bar, n1, n2, and s, or the standard deviation, we would get a value, a t value. But what do you do with the t value? So students' t table is a chart, a t chart that people can plug in their t value and get the p value, which is our probability value. So degrees of freedom basically indicates the number of variables used minus 1. So let's say you have three variables. So your df, or degrees of freedom, is going to be 2. And assume that you have a 5% or a 0.05 test statistic critical value. So your t-test t value is going to be 4.303. If your t value is less than 4.303, you can very well reject the null hypothesis. Otherwise, you would have to accept the null hypothesis. So this way we can refer a t-table and find the p-value or the probability value from our t-test statistic. Now, that was all about t-tests. So what is a z-test? Z-test and t-tests are similar, and both of them just compare the means of two given groups and infer some sort of assumption about them and draw the same conclusions about the population mean. So where is it basically different? Now z-test is has the property that you have to know the standard deviation of the population. In the previous slides, we saw that in t-test, it is fairly simple because you just have to deal with a few samples of the entire population, and then you can actually run the t-test over that, and whatever result you get can be assumed the same for the entire population. However, for z-test, you have to know the standard deviation of the entire population, which makes it quite rare to use in a scientific test or statistical test compared to a t-test. So analysts usually use they usually use t-tests because it's rare that they'll know the population standard deviation. So a z-test is often the first hypothesis test that students learn because it is easy to grasp. Students are taught standard deviation, and z-test does not need you to learn the degrees of freedom or anything more complicated. So it's a very simple test to do in the beginning, but in reality, z-tests are less preferred compared to t-tests. So again, when would you use a z-test? When you're absolutely sure that you know the population standard deviation. If you do not know the population standard deviation, it is always preferred to go with the t-test. So a z-test can also be one sampled or two sampled. So the first formula that we have here, x bar minus mu naught, divided by the standard by the variance, which is again divided by the radical or the square root of n, or the number of samples. So this is our sample mean. Mu naught is the sample mean, and okay, the x bar is a sample mean and mu naught is a population mean. And for two samples, you can see that it is similar to the t-test formula, but the difference that we have here is instead of standard deviation, the standard the population variances are used over here, which is, in practicality, it's very difficult to find the entire population variance. So again, the z-test also has rejection regions, which are defined by the type of test that is used. So let's say in this example we have, if it's a two-tailed test and the significance level is 1%, when you're absolutely sure that you want to dial down or reduce the amount of randomness in your data, the critical values are 2.56 to a negative 2.56. If your test is more over like a left tail test or a right tail test, it is going to be around 2.326, and if it is a left tail test, it is going to be negative 2.326. However, if you go and choose a 5% rejection region or a significance level, you would the values would decrease, offer more allowance for a little bit of randomness. So 1.96 usually is what is the value for two-tailed Z tests, and the left tail and right tail test would be closer to 1.65 and a negative 1.65 for a 5% significance level. So basically, this was all about t-tests and z-tests. Let me know if you have any sorts of doubts or any clarifications, or if I was wrong anywhere, just please let me know in the comments. So these are all the websites that I used for all the pictures and all the information that has been used in this presentation. So thank you, and keep learning statistics.